Hello, esteemed colleagues and participants of the 7th International Conference of Contemporary Affairs in Architecture and Urbanism. Today, I am excited to share with you my research titled Innovative Design Synthesis: AI-Driven Solutions for Sustainable Urban Planning, where we delve into the development, evaluation, and insights gleaned from cutting-edge AI-driven approaches in shaping the future of urban environments. The presentation will cover the context, literature review, methodology, results and discussion, limitations and conclusions. In a world grappling with rapid urbanization and pressing environmental challenges, the need for sustainable urban development has never been more critical. Traditional urban planning approaches struggle to balance competing interests, prompting a search for innovative solutions. This research identifies the integration of advanced AI techniques as a promising avenue to address this gap, aiming to revolutionize urban design and planning practices. By developing and evaluating an AI-driven model capable of detecting urban problems and proposing sustainable solutions. The research question is then, how can advanced artificial intelligence, AI techniques, be leveraged to develop innovative models that address urban challenges? Our research objectives are, first of all, to develop an AI-driven model to detect and solve urban problems. Secondly, to assess the model's efficacy in addressing urban challenges and evaluate the model's performance. And finally, to contribute to the ethical discussion on AI integration in urban planning literature review. In exploring the intersection of artificial intelligence with architecture and urban planning, we uncover significant developments shaping the built environment, notable projects and innovations. Architectural marvels like the Metropole Parasol in Seville demonstrate the power of generative algorithms, while initiatives like Singapore's smart city projects showcase AI's impact on urban infrastructure optimization, impact on sustainable design solutions. AI tools and algorithms play a crucial role in optimizing building performance and reducing environmental impact, enabling architects and urban planners to create more eco-friendly spaces. The advent of digital twins further enhances real-time monitoring and simulation for sustainable urban development. Patterns and applications in research. Researchers emphasize AI techniques such as machine learning and reinforcement learning to optimize urban design and tackle complex challenges. Integrating human expertise with AI capabilities leads to innovative and sustainable solutions. Contradictions and challenges. Despite AI's potential, adoption rates vary among professionals, highlighting skepticism and uncertainty about practical applications. Addressing these challenges requires further research and awareness-building efforts. Methodology. In our methodology, we begin by outlining the process of model development, starting with the utilization of the UC Merced land use dataset. This dataset, containing 21 classes of land use images, each with 100 images measuring 256 x 256 pixels, provides the foundation for our research. These images were meticulously extracted from the USGS National Map Urban Area Imagery Collection, ensuring their relevance to our study. Moving on to pre-processing, the dataset underwent several essential steps to prepare it for model training. Resizing, data augmentation, including random rotations, flipping, and color jittering, and normalization of pixel values, were applied to enhance the dataset's quality and diversity. For model evaluation, we designed a structured questionnaire to assess the generated designs using both technical and urban metrics. These metrics included accuracy, precision, recall, F1 score, confusion matrix, feature importance, as well as urban sprawl detection rate, urban decay detection rate, infrastructure deficiencies detection rate, and environmental degradation detection rate. In terms of population selection and data collection, we targeted a diverse group of 200 individuals, including researchers, developers, architects, and urbanists, to ensure comprehensive insights. The questionnaire was distributed electronically, and data collection was conducted over a specified period. Following data collection, we meticulously prepared and analyzed the data. This involved cleaning the collected data to address any inconsistencies or missing values, coding responses for analysis, and conducting descriptive and statistical analyses, including correlation analysis. Model performance. In this model performance testing, the main prompt instructs the model to analyze an image and determine the presence of specific urban problems, providing reasoning for each assessment. 3 examples are provided to illustrate the model's responses. The model's performance in detecting urban problems shows both strengths and limitations. In the examples provided, it accurately identifies urban sprawl based on visual cues like the density of parked cars and houses, indicating population growth and expansion. However, it struggles with identifying urban decay, infrastructure deficiencies, and environmental degradation, often relying too heavily on surface-level observations without considering deeper contextual factors. Model evaluation. To evaluate the performance of the urban problems detection model, a questionnaire was distributed, and out of the 200 sent, 132 were completed and returned, yielding a response rate of 66%. The analysis of the responses is divided into 3 main sections: demographic characteristics, technical metrics, and urban metrics. Demographic characteristics. The demographic analysis of the model evaluation questionnaire reveals insights into participant characteristics. With a response rate of 66%, the study shows diverse representation across age groups, gender, education levels, and countries of residence. Most participants are aged 25 to 44, with a relatively balanced gender distribution. The majority hold bachelor's degrees, and respondents come from various countries, indicating a broad geographic scope and a diverse pool of perspectives in assessing the urban problems detection model. Participants came from various countries, with the highest representation from Romania, 15.9%, followed by Algeria, 14.4%, and Egypt, 12.1%. Technical metrics. Analysis. The evaluation of the urban problems detection model revealed a range of perceptions among participants regarding its technical metrics. The technical metrics analysis showcases diverse perspectives among participants regarding the model's performance. While a significant portion strongly agrees with its accuracy, 27.3%, and precision, 22.7%, there are notable percentages expressing disagreement. Similarly, opinions on recall and F1 score vary, with some strongly disagreeing, 17.4% for each, and others strongly agreeing, also 17.4% for each. Understanding the confusion matrix and interpreting feature importance elicit mixed responses, indicating varying levels of understanding and interpretation among participants. These findings highlight the complexity of evaluating technical metrics and the importance of considering diverse viewpoints in assessing model performance. Urban metrics analysis. The assessment of urban metrics unveils a spectrum of perspectives among participants regarding the model's efficacy in identifying specific urban issues. The analysis of urban metrics reveals a diverse range of viewpoints among participants regarding the model's ability to identify specific urban issues. While a significant portion strongly agrees with the model's efficacy in detecting urban sprawl, 25.8%, and urban decay, 28.8%, there are also notable percentages expressing disagreement. Similarly, opinions on infrastructure deficiencies, detection, and environmental degradation detection are varied, with some disagreeing, 23.5% and 28.0% respectively, and others strongly agreeing, 17.4% and 22.0% respectively. These findings highlight the complexity of evaluating urban metrics and the need to consider diverse perspectives in assessing the model's effectiveness in addressing urban challenges. Correlation analysis. The correlation matrix provides insights into the relationships between different variables. Here's a summary of the results. Accuracy and F1 score. There is a positive correlation, suggesting that as accuracy increases, the F1 score tends to increase as well. Precision and infrastructure deficiencies detection rate. A negative correlation indicates that higher precision is associated with lower rates of detecting infrastructure deficiencies. Recall and F1 score. A positive correlation indicates that higher recall tends to be associated with higher F1 scores. Understanding of confusion matrix and urban sprawl detection rate. A negative correlation suggests that better understanding of the confusion matrix is associated with lower rates of urban sprawl detection. Interpretation of feature importance and environmental degradation. Detection rate. Another negative correlation indicates that better interpretation of feature importance is associated with lower rates of environmental degradation detection. Conclusion. In summary, this study elucidates the performance and perceptions of an urban problems detection model, revealing varying opinions on technical metrics and urban issues detection among participants. Noteworthy findings include the significant positive correlation between accuracy and F1 score, R 0.216 p 0.05, as well as the significant negative correlation between precision and infrastructure deficiencies detection rate, R shear 0.174 p 0.05. These findings contribute to both academia and practice by providing insights into model performance and highlighting areas for improvement in urban problem detection. The implications of this research extend to the field of architecture and urban planning, where AI-driven decision-making processes can benefit from more accurate and reliable detection models. Moving forward, addressing limitations in data availability and model complexity is crucial, alongside prioritizing ethical considerations